Good afternoon, everyone. Again, I'm Dr. Wallad, and this is the fourth and final installment in the Intro to MRI lecture series. We've already gone through a lot of the basic topics, the intro to the basic physics, how spatial localization is achieved, how we can manipulate the image quality, and what the signal-to-noise ratio means. And then today, I'm going to get into some more clinical stuff, what the basic sequences are, spin echo, gradient echo, fast spin echo, and how we achieve different image weighting, like T1, T2, and proton density. Of course, imaging artifacts are embedded throughout as we have gone through this lecture series. So without further ado, well, remember from the last time when we were talking about the signal-to-noise ratio and image quality, that's kind of what our end result is. And there are several things that are within our control, which we can kind of boil down to being the effective proton number that we're capturing inside the bore and how much time, quote unquote, we're spending on imaging. So today's going to be a little more about the things that are within your control. Imaging for the amount of time images actually take, it's a fairly quick explanation. And then some of the things that can affect image quality, but we don't really control for the sake of quality, is going to motivate our discussion of the different sequences. So, let's start talking about some basic protocols. We'll go through the pulse sequence diagrams for each one and how the images get acquired. So let's start at the basic thing. As we've been talking about basic physics, we've been talking about spin echo sequences. That's all I've been talking about pretty much up to this point. So let's review the sequence of events and some terms. All right, again, this is the pulse sequence diagram. Each line basically represents a different magnetic field direction or gradient direction. So X, in our case, this is the frequency encode direction. Y, in our case, the phase encode direction. And Z, in our case, the slice select direction. Now this RF line doesn't really represent a magnetic gradient. That represents the input and output in most pulse sequence diagrams. So the first thing you see right there is the RF pulse, right? And then the same transmitter coil delivers the 180 inversion pulse at half the TE. And then we get an echo, which I've represented with a separate blue squiggle. So in the spin echo imaging, remember we use our slice selective gradient so that we're only exciting this narrow band of frequencies along the z-axis as we apply our 90-degree RF pulse. That develops the magnetization in the XY plane. To that we apply a phase encoding gradient. The 180 pulse helps to refocus all of the spins that are dephasing, and then we apply the frequency encode gradient as we're recording the echo. Now, again, that was the topic of the last three lectures, so it sounds like a lot, but hopefully you remember most of it. Let's look right now at what TE means, right? TE is the echo time. That is the time that you wait until you collect the echo for your MR experiment. So from the 90-degree RF pulse, in this case, to the center of when you record your echo, that's the TE, or echo time, okay? And this is the time that MXY is decaying while you're imaging. All right. So that's the basic pulse sequence diagram for spin echo image. Well, that usually doesn't help people. People often get confused. They look at the pulse sequence diagram and they say, well, is that a whole image? What is that? They don't understand, which I get. It confused me for a very long time. So let's look at how you make one image in a spin echo sequence, let's say with a matrix size of 128 by 128. Okay, so we do all the steps in the pulse sequence diagram. Each pulse sequence diagram is going to represent an MR experiment. So let's call this experiment number 1, right? In experiment number 1, we use the RF pulse to generate the magnetization in the XY plane. We apply the first phase encode gradient. I've made it a little bit yellow near the center. So that's our first phase encode gradient. We do the inversion pulse, and then frequency gradient is on while we collect the echo. We digitize that echo, and that becomes the data for one line of K-space. So MR experiment 1, we've got our first phase encode gradient, and we've added our first line of K-space. Good. Repeat. Okay. So we repeat it. Now we do experiment number 2. In this experiment, the beginning is the same, but notice I've put the yellow lines in a different place, which also explains to you why this phase encoding symbol always looked like, a hamburger or a multi-layered cheeseburger with all these different stacks on it. It's because the phase encode gradient in each MR experiment is necessarily distinct. It has to be different, right, in order to achieve spatial localization, as we talked about 2 weeks ago. Okay, so for the second experiment, use a different second phase encode gradient. The last part of the sequence is performed operationally the same. So you still collect an echo. Now that echo is going to be distinct because your phase encode gradient was different. So that's going to give you your second line. That's 3. Second line of k-space. All right. ... I don't have to stand here and do this 126 more times. We get to the last one, experiment number 128. This is going to be your 128th phase encode gradient. Notice the yellow lines are in extremis over there. And you still collect one echo, and then that echo is going to represent the 128th line that you put into k-space. Okay, any questions? It's kind of a lot to digest, but all right. Now, we talked about the TE within the slice diagram. People oftentimes, I've gotten that question quite a bit. Well, where's the TR on the pulse sequence diagram? That's the trick. You actually can't see the TR on a pulse sequence diagram. You have to see the pulse sequence diagrams next to each other. Because the TR is the repetition time. This is the time that elapses between MR experiments. So the TR time is defined as the time that passes between two RF pulses, whether center or beginning doesn't matter, since the RF pulses are symmetric. Okay, so notice in a spin echo sequence, the number of phase encoding steps is going to determine the number of MR experiments. Those are going to be the same every time, okay? Because you get one echo per experiment, and you need 100, say if this is 128, you need 128 lines of k-space if the matrix size in the phase direction is 128. You need 128 echoes, so you're going to have to repeat it 128 times with 128 different phase encoding steps. Make sense? Good. Okay. So moving on now, acquisition time. As we've talked about, several parameters determine the scan length. The number of steps in the matrix in the phase direction is going to be a major determinant, right? Because that's how many different distinct echoes you have to collect. The repetition time, because that's the amount of time that passes between each of those distinct experiments. And then also the next. Now, if you remember, we talked about next briefly before. Next is if you want to improve your signal-to-noise ratio, you basically collect redundant data. So you repeat the echoes multiple times, and then you average them together. And then if you recall, the signal increases linearly, and the noise only increases as a factor of radical whatever your next is. So when you do next, it's not integral to obtaining an image. Let's say if we're doing 128 matrix, then you do 128 different MR experiments. If your next is 2, then you're going to have to do 256. Okay? Echo train length, that is relevant only for fast spin echo, which we're going to discuss next. Now, a bunch of the parameters that you hear when people talk about MR parameters don't actually alter the scan length. So field of view, the matrix size and frequency direction, the receiver bandwidth, the flip angle, and the TE, which has to be shorter than the TR by definition. Remember, the TE is within a single diagram, and TR is between two diagrams. So those things don't affect the scan length at all. And we can actually calculate how long a scan will be with a relatively simple formula. And I told you last time that that was the only formula I was going to give you. But I also told you in the first lecture that the Larmor equation was the only equation I was going to give you. So I lied again. And so but it's a pretty simple formula. Basically, the acquisition time is going to be your number of steps or the size of your matrix in the phase direction times the TR, the interval at which you repeat experiments. Makes sense, right? And then if you decide you need more signal and you have to increase the next, then you're going to multiply that by a factor of whatever your next is, because you have to do it that many times. Okay, so there are some exceptions here. Now, your number of phase encoding steps. if you're doing a fast spin echo, which we'll talk about next, you'll divide the time by the echo train length. Forget what that means for now. Also, there's some tricks that we can use with k-space. And we could use like a half Fourier acquisition, in which case it would be divided by 2. You can use zero padding, which is kind of the same thing, where you only collect half of or a portion of k-space and just fill it with zeros instead of relying on symmetry. Okay, now, so let's talk about it. Let's talk about the fast spin echo sequence. Here we see it's kind of the same thing. You deliver your 90-degree RF pulse while the slice select gradient is on. That develops transverse magnetization in the XY plane. You have the 180-degree refocusing pulse, and you apply a phase encode gradient to that pulse for spatial localization in the Y direction. And then your frequency encode gradient is on while you record the echo. Now, notice wow, that actually timed correctly. Sorry, I just impressed myself. You'll notice that the first half of this is actually exactly what a spin echo sequence is. So this is the spin echo pulse sequence diagram from 2 slides ago. But in fast spin echo, there's more. So basically, what you can go on to do is rewind the phase encode gradient that you used for your first echo, apply another 180-degree pulse. Remember, because these spins are dephasing, you apply the 180, they rephase, and you image. But they go past the rephasing and start dephasing again. So you got to do the 180 again and let them dephase and rephase. So, okay, sorry. So you unwind the phase encode gradient, another 180 pulse. Now you apply a different phase encode gradient. So keep in mind, this is your second phase encode gradient. So this is kind of like you're kind of cheating the system here. In a spin echo sequence, you would have had to repeat the 90-degree RF pulse. You had to wait a whole TR, repeat the RF pulse, and then apply your second phase encode gradient. So you can see why this is called fast spin echo. It's much faster. We're already collecting our second line of k-space. It hasn't even been a single TR, and we're still using the same 90-degree RF pulse. And then I've drawn it out so that in this case we get 3 different echoes, right? So this is a fast spin echo sequence with an echo train length of 3. So let's look at this now. The definition of TE changes a little bit here. The TE, you recall, is the echo time, the time between the RF pulse and when you collect that echo. Now, if you're just straight filling into k-space normally, your effective TE is going to end up being basically in the center of all of the echoes that you collect. This is a little bit more advanced, but you can specifically order the way you enter data into k-space. So, and we'll see this in a little bit. So that, because your first echo is the biggest, right? There's still, even though you're dephasing and rephasing with the inversion pulse, so you're getting echoes on the order of T2 decay instead of T2 star decay. I hope you're following me. You're still going to be losing signal according to the T2 time constant. All right. So if you are reordering, your k-space filling differently, then that can actually change your effective TE. So if you're, say, putting this first echo into the center of k-space, and these 2 are more peripheral echoes, that will bias your effective TE towards a shorter time. That's a very complex thought. Any questions on that? I know, probably the first years are just let it go. Don't worry about it. You got to hear this. You got to hear it 4 times. I say this all the time. You got to hear it 5 times, and then eventually it starts to sink in. Okay. So the other parameter when we're looking at fast spin echo is the echo train length, which is abbreviated by ETL, and in this case it's 3. Right? If we collected 4 echoes, the ETL would be 4, 5, 5, etc. Okay. Did I say everything I wanted to say? I think so. Okay. And again, notice each successive echo becomes smaller. Should have clicked the button. This would have been helpful when I was trying to explain that before. Right? Every time there's an inversion pulse, these things refocus, inversion pulse refocus. So we're effectively getting echo heights here, here, and here, even though the natural free induction decay after the RF pulse is boom, you get to 0 signal, before you'd even get to your first TE time. Cool? Good. All right, so just like we did for spin echo, let's look at the formation of one complete image for a fast spin echo, which let's say the matrix is now 129 by 129. I chose that number instead of 128 because it's divisible by 3. We'll just make the math easier. All right, so now in experiment number 1, we have our first phase encode gradient set, right? So you have phase encode gradient 1, 2, and 3, each of which will give you 3 distinct echoes, which you can then place into k-space as your first, second, and third lines of k-space. Notice that you don't have to make that your first line of k-space, second, third. We'll talk about that in a second, how you can put them anywhere. Now, experiment 2, you see where this is going. Now your second RF pulse and your second phase encode gradient set is actually your 4th, 5th, and 6th phase encoding steps, each of which provides you with a distinct echo, which will provide you with your 4th, 5th, and 6th filled lines of k-space. Yada, 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 as Seinfeld would say. And you get to experiment number 43, and that's your 43rd phase encode gradient set, which is phase encoding gradients 127, 128, and 29. And those 3 distinct echoes give you k-space lines accordingly. Now, notice we got the TR. It's defined the same way as in a spin echo, except for before in a spin echo, you only got 1 echo per TR. Here, look, you get 1, 2, 3 echoes per TR. So you get an echo train length number of echoes per TR. So that's still the repetition time, but notice now that the number of MR experiments is not equal to the number of phase encoding steps. There's 129 phase encoding steps, but only 43 experiments. That's where your time savings come from, because it's going to be 3 times faster. Okay, again, this is a little bit beyond the scope. This is what I was trying to say before, right? If your biggest echoes are the first one, and then you're decaying going out there, and just take it as truth for now, the center of k-space is the most important thing to your image. It would behoove you, actually, instead of, say, putting these 3 echoes into lines 1, 2, and 3, which are all in the center, to put them instead so in your experiment number 1, you put this first echo in line 1, the second in line 44, and the third in 87. And then the second would be, yada, 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 until that way your first echoes, the strongest echoes, give you the 1st through 43rd or central lines of k-space. Largest echoes, most signal. Remember, signals are currency, gives us the most imaging quality so that we have an adequate imaging representation of real space, which is the cancer in the patient that we're looking for. Right? Good. Everyone looks happy. I like that. All right, so acquisition time, this is the equation. It's basically the same thing, except for there's an echo train length on the bottom. So again, your number of phase encoding steps times the TR times the MEX. And that's your base scan length, and what the scan length would be for a spin echo sequence. And if it's a fast spin echo, you just divide it by the echo train length, right? Okay, and then remember, you can still do fun stuff to accelerate the imaging. That's beyond the scope of what we're going to talk about here. Okay. Now, what if we wanted to go even faster? So remember back to the animal race, which, if you didn't see the first few talks, you're probably thinking, like, what the hell is going on? But when we have the slower spins and the faster spins, and then you give the inversion pulse and you wait for them to rephase, where you're doing a whole lot of sitting around waiting for those phases to come, for those spins to come back into phase before you can image. So you might ask yourself, well, is there a way that we can kind of force the spins to rephase instead of waiting for them to do so? And, of course, the answer is yes. That, in fact, is exactly what gradient echo imaging is, or gradient recalled echo imaging, or GRE. You'll hear it called all 3 things. Okay, so this is the base gradient echo pulse sequence diagram. I've drawn it this way on purpose because a lot of people kind of make them all the same size, and it doesn't give you the scale of what's happening. Well, I've drawn it in this scale so that you can see just how much faster gradient echo imaging is. All right, so what's happening here? All right, we got our flip angle, which is probably not 90, which is why I've now labeled the RF pulse with an alpha. So it's going to be probably a partial flip angle. You got your slice select gradient, your phase encode gradient, and your readout gradient. But let's look between these red lines so you can see, because everything's kind of crammed together here. At the same time, if you recall, we have to rephase in the z direction because the dephasing that happens during our slice select. Right, we can apply our phase encoding gradient at the same time that we're rephasing in the z direction, and we're applying this negative read gradient and it looks very large, right? So why the hell are we doing this, right? Didn't I teach you that if you apply a gradient, especially a large gradient, to the spins, it's going to completely destroy the signal, right? Well, yes, that's actually exactly what we're doing. We're doing it on purpose. When we do this, it actually destroys all the phase coherence in the sample. Immediately after the RF pulse is applied, you have coherent spins in the XY plane, and this strong negative read gradient just completely dephases them, so you have no signal. But, kind of like in the animal race or in dephasing rephasing, the fact that you've applied a linear gradient in order to dephase them means you've dephased them in a predictable way. Anytime you dephase in a predictable way, it's possible to reverse that. So, if after this strong negative read gradient, I apply a forward read gradient that has the same integral, which is a complicated way of saying same product of strength and time that it's on for, then you're going to take those spins, which were coherent, and you completely wash to zero. And then when you'll turn that gradient on, they'll rephase by themselves. Okay? So that process of rephasing is what forces that echo. Now, the forced echo is also called the recalled echo from back when it was first talked about. And that's where the name GRE comes from, gradient recalled echo. Any questions on that? All right. So gradient echo, right, now let's talk about the different terms that we have to think about with gradient echo. Here's the flip angle alpha, so it's going to be less than 90. We'll talk about that a little bit more. The TE is going to be the same, defined the same way as the distance between the RF pulse and the center of the echo that you collect. Of course, in this case, the TE is going to be much smaller. What was I going to say? Yes. So, and then again, just note that that's it. That's the whole unit experiment. It can be very, very short. It's often times way, way shorter than the spin echo. So sometimes people will draw gradient echo diagrams like this, which will usually confuse people. Because really, this is just 1, 2, 3, 4 different gradient echo experiments, but put on the same page. So you have to be wary of that because, within this pulse sequence diagram, not only do you see a TE, but you also see a TR from RF to RF. Okay? So if we're doing a 129 by 129 matrix with a gradient imaging protocol, basically we do this 43 times. Now, the fact that it's 43 times, that's just because this is all that fits on the screen. Imagine that this phase diagram just extends off the screen, and out into the parking lot until it's 43 times its length. Okay, so it all happens one after the other. We have our TR, like I said, which is the repetition time. Now notice the number of MR experiments is again equal to the number of phase encode gradients, just like it was for a spin echo. Okay, there's still going to be 129 experiments, but this is going to happen a lot faster than it did with 129 experiments for the spin echo, because you had to sit around waiting for the rephasing 180-degree pulse to take effect. Okay, so the equation for acquisition time for gradient echo imaging is, no surprise, the same as that for a spin echo sequence, right? Number of phase encode steps times the repetition time times next, except we can basically ignore the next because the number of experiments is always going to be 1, really. I mean, you can change it, but the whole point, the reason we're doing gradient echo imaging is because we need it to be fast, right? Maybe we need to do it within a breath hold for the patient. Maybe it's, there's a bunch of reasons why we want sequences to be shorter. So, if we just want signal, we might as well use a spin echo or a fast spin echo instead of a gradient. But anyway, so oftentimes you'll see when people talk about the imaging time for gradient echo, they won't even include next. They'll just say number of phase encoding steps times TR. And again, keep in mind, there's case-based things that we can do to change the imaging time and make it even less. But hold that thought for a second. You might say, when we talked about the spin echo, and then we talked about the fast spin echo as a means of acceleration. Well, can I take a gradient echo and then accelerate that even further in the same manner, i.e. by getting multiple echoes per RF pulse. Yes, but there's a caveat to that. And that caveat is basically you're never going to get more than 2, 3, 4 echoes per RF pulse in a gradient recall echo acquisition. Why is that? Well, it's because, remember, with a gradient, since there's no refocusing pulse, our signal decays as free induction decay, right? It doesn't come back up like we saw in those nice graphs after the 180-degree pulse. So, you know, the T2 star is going to make it degrade so fast, you're just not going to be able to do an echo train length of 16 because there's just not enough signal to do that realistically. And then, of course, there's no refocusing to boost the signal. By definition, else it would be a spin echo sequence. Okay. If you really want to push the limits of speed, there's an extreme sequence which is similar to gradient echo imaging in extremis, which is called echoplanar imaging. But we won't talk about that here. I'll save that for the advanced sequence lecture. Okay. Now, back to K-space. I keep throwing it in there. I know everyone hates it, but here's a picture of K-space. Remember, we talked about it before. K-space is not, or should not be scary. It's just a plot. It's an XY plot, right? Smaller numbers in the middle, bigger numbers are on the outside. Remember, K-space corresponds to spatial frequencies. So think back to our books on the bookshelf and what spatial frequency means. So low spatial frequency information are big changes over the image, right? That's what we call contrast or image fill, right? And that's the low spatial frequency information. That's why I say, and everyone says, that the center of K-space is the most important part of our image acquisition, which is why you may want to reorder or pay a lot of attention to how you're ordering K-space entry. Out in the periphery, at larger values of spatial frequencies, that's where we have high spatial frequency features, which, if you recall from our lecture, edges are a high spatial frequency feature. Noise is a high spatial frequency feature, right? Think about it. Every individual pixel we have has noise in it, right? And because you get noise with every independent measurement, and noise is, again, statistically independent. So if I were to try and image, say, a gray flat field that should just be all one value of gray, well, every pixel in that field is going to be a little off by some number, which is noise, and that noise should not be correlated, oversimplified, with other pixels, right? Think about the spatial frequency. If spatial frequency is how things change over distance, what's the most something can change over distance in your image? Every pixel, right? If you had black, white, black, white, black, white, every other pixel, that's the limiting spatial frequency of your imaging space. That's the most you can have. So if you can remember it that way, noise is on a per pixel basis. Thus, it is a high spatial frequency feature. You'll remember that noise is in the periphery, in the high numbers, and image fill or contrast is in the low numbers, low spatial frequencies. Now I know that's a lot to just talk through, so I have this picture, which is my favorite picture of all time because it describes it so well. This is not mine, and I apologize. I put this into my talks years ago, and so I don't have a reference for it, but this is a great way to look at it. So in the center here, we have, this is literally the K-space representation of this photograph of an airplane. Okay, now let's notice a few things about the K-space here. There's a lot of information or brightness in the center at the low spatial frequencies, and that's because the low spatial frequency information is really what's giving us the fill of the picture. Okay, now you see these like prominent lines along the x-axis and the y-axis, and those correspond to horizontal lines and vertical lines. Well, you know, we have a lot of horizontal separations here, right? We have foreground and sky. This is literally such a low spatial variation that it's dark in one half of the picture and light in the other half. That's the lowest spatial frequency you can have along the vertical direction. So that's going to be, you know, all this information in the center. Also notice that it's symmetric, which is something I've said about K-space before. But now, more interestingly, let's look at the different parts. So you can actually filter this out. If we cut out the periphery of K-space, we're essentially removing the high spatial frequency information. So let's see what happens. Okay, now we're looking at this plane Well, it looks really blurry, right? That word blur is going to be very important when you start looking at X-rays and CTs and talking about spatial frequencies there. But for now, notice that it's all low spatial frequency information. It's contrast, it's image fill, right? Try to read these letters, the HA. You can't really read it there because it's not, there are no sharply defined edges because those have been excluded. Now let's do the opposite, and let's cut out the center and only display the periphery of K-space. Well, that's where all the high spatial frequency information is. So now we don't have any of the fill. You know, we don't know if this were color, like what color the grass is or the sky is or anything like that. All we see are the edges. Does that make sense? Any questions on that? I'm belaboring the point, I know, but K-space is very challenging for people. All right, so like I said, K-space is symmetric. So now I'm going to tell you a little bit about the, our half Fourier acquisition. So technically, if you have half of K-space, say 128 by 128 matrix, if you were to take 64 lines, you can mathematically recreate the other 64 lines. Okay, but remember I said the center is so important, so vital for us to get a good image, we're going to want to oversample the center. So people take more than half, let's just say 68 out of 128. And when you slightly oversample like that, well, you can get away with just getting 68 lines, and you compute the other mathematically. That's math, baby. Math, baby. Yeah, you like it. All right, so yeah, this will cut your acquisition time basically in half. So it's great. We love it. All right, now for some interactive questions. All right. If I did a spin echo T2 sequence with the above parameters, how long will it take to acquire each image? So at the top, you see all the parameters. There's a lot of them, but I think it's important to be able to pick out the salient information from all the noise, the signal to noise, as it were. If you can't read those values, I'll give you the salient values in the way of a hint. TR is 1,000 milliseconds. Matrix size is 128 by 128, and the next is 1. This one. All right, good. Most people got it correct. So it's 2 minutes, not 1 second. Let's take a look at a little closer look at the question here. If we remember our acquisition time equation, it's the number of phase encoding steps times the TR times the next. The TR is 1,000 milliseconds, which is 1 second, right? So 1 second times number of phase encoding steps is equal to the matrix size and the phase direction. That's 128. So it's 128 seconds times next, which is 1. So still 128 seconds is about 2 minutes. 120 seconds, 2 minutes. Okay. Questions? All right. Now, if I did a fast spin echo sequence with the above parameters and an echo train length of 8, how long will it take to acquire each image? So by way of, if you can't read it, or giving hints, since this is just for educational purposes, not trying to actually test you, the TR is again 1,000 milliseconds. The matrix size is 128 by 128 again, and the next is 1. So it's the same parameters as the last one, except it's a fast spin echo with an echo train length of 8. Yes, 100% got it. Very good. So about 16 seconds. So it's the same as last time, 2 minutes divided by the echo train length, 8. 2 minutes divided by 8 is about 16 seconds. Very good. I'm sorry, 16 seconds exactly. All right, now, if I did a fast spin echo sequence with the above parameters, where are my parameters? Sorry. Okay, and an echo train length of 8, but I use a half Fourier acquisition. Now about how long will it take to do each image? Again, the TR is 1,000. Matrix is 128 by 128. The next now has increased to 2 relative to the last ones. Let's see what we got. Okay, so most people still got it right. It's actually 16 seconds again. Well, last time it was 16 seconds, right? So this time the next increased to 2. So we doubled the imaging time to about 30 seconds by having a next of 2. But then by doing half Fourier acquisition, we knocked it back down to about 16. Cool? Good. Now match up the pictures, the K-space pictures with the images that they would produce. So this is like our airplane picture, but with something a little more clinically relevant. About a slice through the lower chest here.
At least from back here, 2 and 3.
Yeah, it's not projecting well. Thank you for pointing out. 2 is blurry.
Okay.
2 is much blurrier than 3. Yeah, that doesn't project well at all. Sorry about that. Yes. Yes, most of you got it correct. Yeah, so A is 3, B is 2, and C is 1. Right. So the entirety of K-space will give us the nice picture, which I had to tell you, you can't tell. It has both the image contrast and the edge information. Just the center of K-space is the low spatial frequency information. That's image contrast or image fill. So that's going to be your general structures, hearts here, fats there, but no edges, so it'll look blurry. And then the periphery of K-space is the edge information, which is number 1. You don't know what's filled in and what's not, but you can see the edges. Okay. Now, so we talked about many causes of signal change in our SNR lecture, right? There's a bunch of things that we can change that change the effective proton number, like field of view, the matrix size. We talked about some things that we can change to reduce the noise, like increase the number of necks, reduce our receiver bandwidth. There's some things that can't be changed, like the B0 of the magnet, or the proton density of the actual tissue that you're measuring. Remember, those are that K factor in the second only equation that I wanted you guys to remember. Now, other reasons that the signal could be increased would include the echo time. Right? The longer you wait to collect an echo, the more your spins are going to dephase, the more signal you're going to lose. Right? So a shorter TE will give you more signal. Right? Flip angle, well, if you're using a very small flip angle, you're going to barely be putting any spins into the XY plane. And if you use a 90, then you put all of them into the XY plane. So the larger your flip angle gives you more tipped protons, gives you more signal. Okay, repetition time also affects actually your signal to noise ratio, because the longer TR you wait, the more tissues will recover between experiments. And the more longitudinal magnetization recovers, the more you will subsequently put into the XY plane with subsequent RF pulses. Okay. Even though it is true that those 3 things affect your signal to noise ratio, don't think about them that way. You should not think about them that way, because those are the things that we use to determine what kind of images we're seeing. Is it a T1? Is it a T2? Is it a proton density? So because changing those things will completely change the image weighting of your sequence, you can't rely on those for changing your signal to noise ratio. Okay, just a quick check here. Which of the following would improve your image quality by increasing the effective number of oscillating protons being measured? Is it if you lower B0? Is it if you use a longer TE? Is it if you use a longer TR? Or is it if you use a lower flip angle? So I want you to think. Only one of these things would actually increase your SNR ratio, even though I just told you not to think about it that way. I say, good. Most of you got it correct. Exactly. A longer TR. And that's, again, I'll repeat myself, the longer you wait between experiments, the more MZ, which is the longitudinal magnetization, recovers, and the more potential magnetization you have to tip into the transverse plane with the subsequent RF pulse. I like saying things over and over again in slightly different ways because I think it helps it too. So, all right, sanity break. I think we should take a little 2-minute break. We're at the midpoint. Welcome back, everybody, from the break. We talked a little bit before the break about the different the main basic sequences: spin echo, fast spin echo, gradient, and multi-echo gradient, which is is what it is. And then we're going to spend the second half of this talk discussing basically how we get image contrast, or how images are weighted. Now, many people struggle with this concept. They ask themselves questions: what is T1? What is T2? What's a flip angle? What is PD? I didn't, certainly for years, didn't understand any of this stuff because, I never got a straight answer when I asked about it, frankly. Well, the thing to note is this is the core advantage of MRI, right? It's going to help you resolve different tissue types, because whereas, say, if you're looking on a CT, right, CT really is only measuring the density, more specifically the linear attenuation coefficient of tissues. So if the densities of two tissues are similar, they're going to look about the same on CT, which is why you can't see anything in a non-contrast CT if there isn't sufficient, say, intraperitoneal fat to provide contrast. The T1 and T2 characteristics may not be the same for two tissues of the same density. So two things you cannot tell apart on CT, you may be able to tell apart on MR. Again, that's the nice thing about MRI. So, all right, let's review the basic definitions and then go into a little more detail after that. Okay, T1, remember, T1 is a time constant. That's all it is. It's measured in a unit of seconds or milliseconds, and it's the amount of time it takes to gain 63% of longitudinal magnetization in the z direction after a 90-degree RF pulse. Okay, T2 is actually is also a time constant, also measured in seconds or milliseconds, and it's a time constant that describes or fits a curve. And is how long it takes to lose 63% of your transverse magnetization due to dephasing from, T2 effect after an RF pulse happens. Any questions? Those are the two founding principles you actually absolutely have to know. Now, I say if you feel lost or forgotten, let's review the basics, and that's because this lecture was initially, given months apart from the other lectures. But first, we will go into my favorite analogy, which is that MRI is like a toilet. Okay. Figure this might help you get a handle on things. Might be a little bold of an analogy. With a W. All right, fine. MRI is like a toilet. Let's go through how this works. All right, so assume that water is your magnetism, okay? Now, there's a false assumption in a real-world toilet. There's always water sitting in the bowl. But let's pretend that the bowl is empty at baseline, okay? So all the water, i.e. magnetization, is in the tank at baseline, and the bowl is empty, okay? Now, the handle, the flusher, is going to be your transmitting antenna. So flushing the toilet is like sending out an RF pulse, right? When you flush the toilet, the tank, which represents MZ, or longitudinal magnetization, where the water / magnetization is stored, that water will drop to zero when you flush, right? The tank empties, okay? Part number two that's not quite accurate, a real-world toilet, but we're not plumbers, is that let's just say that the water goes directly from the tank into the bowl. The bowl is going to represent the transverse magnetization, the MXY. Okay, so RF pulse, you hit the flusher, MZ empties, and MXY appears as magnetization. Okay, and it decays rapidly in an oscillatory manner, just like a toilet bowl drains. Okay, and that's free induction decay. Now the fifth step is back to the tank, which is MZ, or longitudinal magnetization. The water in the tank will slowly fill back up again, right, which represents T1 relaxation, or the magnetization rebuilding in the longitudinal direction, getting ready for the next flush. Now keep in mind that the way different tissues are, the toilets can all be different, right? Let's say if your water hookup is high pressure versus low pressure, right? If the opening between the pipes has a large cross-sectional area versus small. If the drain on the toilet bowl is small or large, if there's a bigger tank, smaller tank, more water, more magnetization, all these things have corollaries in the real world. But when we're thinking about an image, basically each voxel is like a little toilet. So every one of these voxels will act independently because they all have different size bowls and different size tanks and different size hookups and different size water flows, which will result in tissue heterogeneity, which is why when we take an MRI image, it's not just a gray field, right? Now, I have to give credit to Thomas Macaulay, who is one of the people who taught me MRI initially. He's a great man, brilliant man, does a lot of MRI research, and is also an associate professor at Yale. Okay, so now I said let's revisit our first lecture. Again, we don't really have to go through this because since we've been doing it pretty quickly, just a reminder, there's net magnetization in the z direction, right? That, we've been through this a bunch of times. That magnetization rebuilds, of course, according to T1. T1's a time constant that fits that rebuilding curve, or T1 relaxation. The RF pulse only works when it's oscillating at the same frequency of the protons. It'll rotate the magnetization from the z-plane into the xy plane. Depending on the strength of your RF pulse and how long you leave it on for is what will determine your flip angle. If you only leave it on for a short time, you get a partial flip angle. If you leave it on for the exact right time, you get a 90. Twice that time, you get a 180, okay? And then, of course, there's T2. Once you develop transverse magnetization, it rapidly decays according to T2 or T2 star, depending if you're using an inversion pulse or not. And basically, the fit of that curve as you listen is according to the T2 time constant. So that's just a real quick one. We've been over the inversion pulse. If you use inversion pulses, things decay as T2. If you don't use the inversion pulse, it's T2 star. Okay, sorry. Rapid review. Now, this is a very important definition because this is like the definition of what contrast weighting is, which eluded me for years. A T1 or a T2 weighted image depicts differences in the time constants, T1, T2, and T2 star, inherent to different tissue types as contrasting levels of brightness in those different tissues within the image that you get. Okay, this is crucial. Anyone doesn't understand this? Raise your hand. Speak now or forever hold your peace. Okay, this is gonna that toilet joke would not be appropriate for this venue. Okay, in a T1 image, let's look at this. Things that are going to be bright are going to be things that have a short T1 time. Now let's analyze this. So T1 describes the rate at which longitudinal magnetization recovers. So if T1 is short, that means it takes a short amount of time relative to other tissues for T1 to grow back. So in the TR, within the repetition time, that is, in the time between two distinct MR experiments where you're collecting different echoes, things with a short T1 are going to regain more signal than things with a long T1, thus giving higher signal. Fat has a very short T1 time. CSF has a very long T1 time. So in a T1 weighted image, we've manipulated these factors, which I'll put in air quotes for now, and we'll discuss that in detail in a few minutes. We've manipulated the parameters to bring out the fact that CSF has a long T1 and fat has a short T1. That's all that a T1 image is. It's showing the T1 characteristics of different tissues relative to one another. Okay, same definition of tissue weighting. Think about T2. In a T2 image, bright things have a long T2 time. Okay, this used to trip me up a lot too, because right in a T1, it's the opposite. It's with a short T1. Well, it's because T1 describes growth of longitudinal magnetization and T2 describes decay of transverse magnetization. That's why they're the opposite. So thinking about this on its own, something with a long T2 means the transverse signal is going to hang around for a long time. It's going to take a while for it to dephase, right? So if you're waiting, before you collect your echo after your RF pulse, things with short T2 times are going to dephase and their signal is going to drop away. But those things with long, tenacious T2 times are going to hold on to their coherent signal, and they're still going to give you signal when you finally collect that echo, i.e., they will be bright. That's how you get bright things on T2. So for example, CSF, like we said, it had a long T1. It also has a long T2, a very long T2. So if we use a long echo time, we're going to see CSF really brightly, whereas, say, white matter has a pretty short T2. So white matter is going to look relatively dark when we get that, when we wait a while to get that echo. Okay, it's not quite so simple because the two interact, but we're going to go over that in a second. So that's what we're going to do now. How do we make a T1 or make a T2? And it's by manipulating the different parameters in order to isolate the differences in T1 and T2. Okay, so the echo time, think back to the toilet. Now the echo time is how long you wait after flushing, after the RF pulse, to see how much water is in the bowl. Okay, the TR time is how long you wait before the next RF pulse, how long you wait before it flushes. Now in the real world, you can equate this with, if you flush a toilet and then you try to flush it again right away, you won't even get a flush because the water hasn't rebuilt. In the imaging world, that's like doing a short TR, right? If you have, if you've waited a short TR so you flush and you can't flush again, you're going to get zero signal. But if you have, remember, each pixel is its own toilet. So if you have 128 by 128 toilets, some of those toilets are going to have really big pipes hooked up to their tanks, and that's things with a short T1. So water's going to pour right back in. So in some pixels, you could flush right away. That's where you get T1 signal. Okay? Now the flip angle, that's how much you rotate MZ into the MXY plane. Analogy breaks down a little bit here too, but come on, it's a toilet analogy. So you can't think of it like if you're in Europe and you get the, you have the partial flush versus the full flush, depending on it's one or if it's two, meaning full, oh God. Full flush, partial, not, okay, I'm done. I'm out. Okay, stepping out of the analogy. But in flip angle, basically it's going to be you only take part of the water in the tank and put it into the bowl. So you're not going to have as much signal in the bowl at first at T0, but you're also going to have stored some magnetization in the tank, allowing you to just mash on that flusher, I guess, and flush multiple times in a row. Okay, now let's look at weighting and spin echo sequences. This is absolutely core knowledge that you should have as a practicing radiologist. What makes it a T1 and what makes it a T2 image? So I love Excel. Let's go back to Excel, right? And we're going to model signal growth and decay after an RF pulse. Okay, so we generate a bunch of numbers, and we're going to look at some familiar tissues: CSF, fat, and muscle, which I've just plugged a couple of published T1 and T2 values in there. M0 just represents the relative abundance, which you can think of as proton density. It's just necessary for the calculations to work. All right, looking first above, this is MZ, which is longitudinal magnetization versus time. T0 represents the moment of an RF pulse, okay? So you flush the toilet, the tank's empty, it's at 0, right? These three curves, notice they all look different because they're three different tissues with different T1 times that characterize these regrowth curves, right? So who's our leader up here, this blue curve? Well, that's fat. We already knew that. We said fat has the shortest, pretty much shortest T1 time in the body. So that's, you can see how fat is going to separate itself from CSF very well based on how long you give it to recover. Okay, now as a completely separate graph, let's look at MXY versus time. This is the transverse magnetization on the bottom here. After the RF pulse, all the water appears in the bowl, right? So 100, everything starts at 100, okay? They're all in the same relative abundance, and then they all fall away exponentially according to free induction decay, right? But look at CSF. Remember I said CSF has a really long T2 time, right? It holds on to its signal for a really long time. So you can see how now if you wait for a longer TE, your CSF signal relative to the other signals is going to blow it out of the water, right? That's going to be like T2 waiting, okay? So again, notice long T1 like CSF recovers MZ slowly. Short T1 like fat recovers quickly. Long T2 like CSF maintains your transverse signal the longest, and things like muscle with a really short T2 lose their signal very rapidly. Any questions on this? Good. As long as you're still with me, we're going to see right now how to T1 weight an image. Okay, First things first, you want a relatively short TR. Sounds kind of weird, but if we're trying to manipulate the regrowth, we can't give things too long to recover, okay? We use a short TR so that things like fat with a short T1 time will recover rapidly within our TR, okay? And then things with a long T1 time over multiple pulses, remember, we have to do 128 MR experiments, let's say, to get a single image. So over multiple pulses, things with a long T1 time like CSF will die out because they're not recovering between pulses. Also keep in mind, in the real world, when we do pulse sequences, the machine does a preparation, so it actually does several pulses first and throws them away so that everything reaches equilibrium. Just keep that in mind. Okay, the second part of getting a T1 weighted image is after having a relatively short TR, we use a very short TE, right? Ideally the minimum possible. Well, why do we do that? It's so that we don't allow time for the signals to decay, right? Because things decay on the order of T2. If we're not waiting at all, then we're not allowing T2 to come into the picture, right? Okay, again, this is all words, and then we can see pictures, which will make everything much easier. Here we see multiple RF pulses of fat versus CSF. The fat, you notice, recovers. It doesn't go back up to 100. It goes up about to 80 with each subsequent pulse. But you notice it sets up a really nice equilibrium for itself. So basically, you could do this all day, and fat's going to constantly be coming back up to about 80. But look what happens to CSF or water. Right? As you do subsequent pulses, it's not getting past the critical point where it's able to maintain some sort of equilibrium, right? So there's a critical point here in choosing your repetition time where if it's too rapid, your signal will actually completely decay over time, and you'll have none available even, okay? Now, this is just the basics. Let's look kind of on a broader scale. Okay. We're going to do an actual experiment with actual numbers. We're going to pick a TR of 600, okay? And we're going to compare CSF, fat, and water. Now, notice, again, the fat is the blue. That's recovering very rapidly between sequences. The liver has a short enough T1 that it's able to set up an equilibrium, though it's lower than fat, but it's not going to die out. And the CSF, because it's below that critical point, is just going to die out. And you're going to have basically zero longitudinal signal with each successive RF pulse. So you're not going to be getting any signal from water from the get-go. Okay, that's MZ. Now let's look at MXY. Okay, notice how these curves sort of morph a little bit more over time. We start to get an idea for what the equilibrium is going to be by the end, right? Because the first one, the CSF's way higher, and that's just because it's the first one and there was a ton of signal around. But as CSF dies out, in terms of its longitudinal recovery, it won't contribute even basically at all to the last image. Notice still though, if you waited a really long TE, there's actually more CSF signal than other stuff, even though you're starting with next to nothing. Okay, so now remember for T1 sequence, we have to select a short TE, right? So an echo time of 20 milliseconds will give us this, right? And this works perfectly, right? Because fat is about twice as bright as liver and CSF is dark. That's a T1 weighted image, right? Everyone follow that? This, of course, is like, it's not exact, but it's just a spreadsheet, so. Okay. Now, same thing, except for let's talk about how do we T2 weight an image. All right. So same longitudinal and transverse magnetization. We went through all that the first time. Now let's look. We're going to do kind of the opposite. We want to pick a long TR. Well, and that's for, like we talked about before, if you have a long repetition time, you're going to allow everything to recover between experiments in each TR time. Okay? So whether it's fat or CSF, things are going to be recovering, so it's not going to matter. It's going to unweight the T1 portion. Okay? And then we're going to use the long TE, which we already discussed. If you're waiting around a long time, things with a high T2 are going to have more signal. So now let's look at, as we're setting up our equilibrium, we've increased our TR to 5,000 instead of 600 milliseconds. Now we're waiting 5 seconds. If you're waiting 5 seconds, right, everything's recovering. You'll notice CSF isn't dying out anymore because even though CSF has a crappier long T1 time, we're above that threshold where it can set up an equilibrium for itself. Right? Everyone following me? Good. Okay, so we'll look at sort of the same thing, but again, the TR is now 5,000. So we're waiting a much longer time. The fluid is able to recover, maintain an equilibrium, and then when we look at the transverse magnetization, now everything's basically starting up at 100, or at its equilibrium state. And then if we wait for a longer TE, a slightly longer TE, let's say 1,000 milliseconds, which on the scale of 5,000, it looks about the same distance, that's appropriate. When you use a TE of 1,000 in this case, the CSF is going to be bright, right? The fat is going to be gray, and the liver is darker than the fat. That's a T2 image, right? It works. Math works. That's why I love math. I know no one else loves math in this room, but I love math. Okay. All right, so keep going now. Let's talk about proton density. Again, our model assumed, you remember, we had 100 for everything as the relative proton density just for the sake of explanation. So we're going to have to manipulate that in order to demonstrate this. So let's just arbitrarily set muscle to be 50% proton density of CSF and fat. Okay, so these are the old curves from before. We changed the proton density, and now notice what happens. So muscle can only recover to about 50 instead of 100, right? And when you put an RF pulse where everything goes into the XY plane, you only generate 50. So you're only at T0 generating 50% the signal as you are for CSF or fat. Okay, so in terms of what do we manipulate to get proton density, you want a long TR, right? Because the long TR unweights T1, right? There is no T1 weighting if you're letting everything recover. And then you want a short TE because that unweights T2. So you can think of proton density weighting as not a positive sort of strategy. It's actually the lack of the other two strategies. And that's why there are three of them. And so we look here, setting up over time. Notice that even in extreme, the muscle can only recover to 50% that of fat. So let's look. We've done this. Muscle setting up an equilibrium for itself, remember, can only achieve a maximum of 50% of fat. So we do a TE that's very short as possible, kind of like when we were doing T1 imaging. And so the fat is going to be about twice as bright as muscle. And hey, that's what we said, right? Fat is 100 and muscle is 50. So it works. Makes sense. Everyone follow that for proton density? Good. All right. Here is your summary. If you get confused when you think about these things, and you want to memorize the 2x2 table, which I think is always harder than actually memorizing, learning and understanding the concepts and being able to rederive them, this would be the 2x2 table that you want to memorize. Okay? You talked about these. Notice there's some question marks here. That's because if you have a short TR, right, that's going to T1 weight things, right? And then you have a long TE that's going to T2 weight things. So it don't make sense, because you're kind of like, you're killing both signals. And so you just get a crappy low signal image that doesn't make sense. Cool? All right. Question. Losing my voice. Which of the following is always a true statement? T2 star is greater than T2. T2 is greater than T1. TE is greater than T2. Or TR is greater than TE. So this is, do you remember what the abbreviations mean? And do you remember their relative scales? So let's see, what did people say? Wait, hang on, I have to make sure I know the answer. Okay. Yes, most of you got the correct answer, which is T. Hey. Always one in the audience. Right, so the TR is always greater than the TE. Remember we talked about that when we were talking about the pulse sequence diagrams. TR is between two diagrams, and TE is within the diagram. So by definition, TR is always going to be longer than TE. T2 star is actually the opposite. T2 star is always shorter than T2. T2 is always, or T2 greater than T1. That's the opposite of what is usually true. And TE is greater than T2 is kind of senseless. It's It could be either, depending on what sequence you're doing. Okay? Now, a spin echo MRI is performed with the following parameters. This is everyone's favorite up here. What type of weighting should the image have? I'll give you a couple seconds to figure this one out. Again, it's not a test, so I'll give you some little hints. Remember, the salient things are flip angle, which is always going to be 90 in our discussions of spin echo, fast spin echo, so you can ignore that. TR and TE, right? So in spin echo, we're looking at the TR and the TE. 3,000 milliseconds, 3 seconds. Does that sound like a long time in the MR world or a short time? It's kind of a long time. There you go. And TE, 25 milliseconds, that's kind of a short time. Okay, so what has a long TR and a short TE? I'm giving you hints because I need to figure it out before I hit it. Yes, very good. Proton density, that's correct. 80% of you got it right. It is a proton density. Let's look back at our curve here, right? So proton density is when you have a long TR and a short TE. Long TR unweights T1, short TE unweights T2. In the lack of T1 contrast and T2 contrast, you're looking at the raw proton density in that voxel, which sounds much cooler than it is. Okay? Which of the following is always a true statement? I accidentally gave you the answer to this about 30 seconds ago. I apologize. But is T2 star always shorter than T2? Is T1 shorter than T2? Is TR always shorter than NEX? Or is TR always shorter than TE? So in our shorter thans list, yes, most people got it correct. T2 star is always shorter than T2, right? Some people said T1 is shorter than T2. Well, that's not true. In fact, hang on. Wait for it. In fact, T1 is almost always longer than T2. I don't think you can say always, but so B is usually the opposite. TR and NEX are completely unrelated. NEX is arbitrary, so it doesn't matter. And this relationship is the opposite. TR is always longer than TE, as we discussed 2 questions ago. Questions about the question? Meta questions? Okay. Okay, spin echo MRI is performed with the following parameters. What type of weighting should this image have? Again, I'll point out the salient features here. Flip angle is 90, which we're ignoring anyway because it's a spin echo. The TR is 3,200, so 3.2 seconds. That's pretty long. And a TE of 500 milliseconds. That's actually pretty long, right? Because the TE is supposed to be a short time. So you have a long TR and a long TE. And that should give you, again, I'm figuring that out loud because this stuff's not easy. T2, 100% got it right. Very good. I'm very proud of you guys. Yeah, so it's T2. It's a long TR and a long TE. Refer to our 2x2 table there. Here's a fun one, which some of you may remember from last year, if you were awake. This image that I'm showing you is analogous, or most analogous, to which of the following MRI processes? Frequency encoding, phase encoding, free induction decay, or MZ recovery. This is just, kind of a little brain twister, thinking in analogies. I saw this image on the internet and I had to grab it because I thought it was really cool. The way it so perfectly analogizes with this concept. Let's see what people say. Yes, 100% got it. Yes, that is free induction decay. Very good. I'm very proud of you guys. Oops. All right, yeah, so if you look at the first line, Mary had a little lamb. It's very coherent. And then with each subsequent line, the letters are kind of splaying apart. And by the bottom, you can see that it's actually, say 20 of each letter in light gray that's at the top superimposed upon each other to make a nice heavy black signal. So your signal to noise ratio is very high in the top line and rapidly declines with dephasing. Good? Good. Spin echo. excuse me, a spin echo MRI is performed with the following parameters. What type of weighting should this have? All right, I'll go over the salient features again. Flip angle is 90, which we're ignoring because it's spin echo, so we're expecting that for our purposes. Though in real life, you can have other angles. The TR is 550. It's a little shorter than we've been talking about. And the TE is also pretty short in the numbers we've been given, 19. So relatively short TR, short TE. What does that do for us? Enough answers? Yeah, let's see. T1 weighting, 100%. Got it correct. Very good. Exactly. So a short TR, T1 weights the image, and a short TE, T2 unweights the image. So you have a T1 weighted image. Which of the following has the most precisely defined echo time? Oh, I don't think it's important that you know the TE's echo time. A T2 star-weighted gradient multi-echo sequence, a T1 weighted spin echo sequence, a T2 single shot sequence, or a T2 weighted fast spin echo sequence. Yes, 80% of you got the correct answer, which is a T1 weighted spin echo sequence. So let's talk about this just to make sure that everyone gets it. Where the TE is defined as the space between the RF pulse and the center of the collected echo. In the case of a spin echo sequence, you have one echo per RF pulse. Thus, the TE is precisely defined. Actually, in all the other examples, the TE is not precisely defined. A T2 gradient multi-echo sequence has multiple echoes, so you're going to be using an effective TE value in that. The T2 single shot sequence is tons of echoes. You're actually getting an entire image with one RF pulse, so that's going to have a very poorly defined echo time. And a T2 weighted fast spin echo sequence, again, you're going to have to figure out what your effective TE is amidst that echo train, whether it's just an average or based on where the center of K-space is being filled. Okay. Good. There's another sanity break. We're not going to take a 5-minute break on this one. So we're just going to power through. I think the last part isn't that long. All right, so let's talk about contrast weighting in gradient echo imaging, also called gradient recalled echo imaging, or GRE. All right. Gradient imaging uses small flip angles, okay, and that's so that the MZ doesn't get exhausted with each RF pulse, right? It allows for a much shorter TR, and it gives you still have the option for multiple echoes. So remember the time equations, which we've said is the number of phase encoding steps times the TR. If it's a multi-echo gradient sequence, then it's also divided by the number of echoes in the multi-echo sequence. And don't forget about nex. It's possible, but in a gradient, we're trying to go fast. We're just going to assume that the nex is always 1. All right. Now, what does a non-90 degree flip angle do? Well, think in terms of projections or component vectors, right? Easy to say. Might not make sense to some people, but so we look at alpha is the flip angle, and that's defined as the angle from the z-axis. So here we see this, the net spins have been rotated away from the z-axis by about 30 degrees, qualitatively looking at it, right? So it's from the z-axis, not from the xy plane, right? And that's going to be the flip angle. Now, what happens is, talking about projections, pretend I'm holding a flashlight over the top along the z-axis, right? What's the shadow of this vector going to be? That's how you think of what the component in the plane that the flashlight shines on is. So the xy component is going to be, the shadow of this vector on the xy plane when the flashlight's above it. That's going to be related to the sine of alpha, right? If here's alpha, this is your 90-degree triangle. SOHCAHTOA, sine opposite over hypotenuse. Yeah, bringing back some good memories for people. Love trig, gotta love it. That's great. I know, you all hate me. Okay, and then MZ is partially preserved, right? So now think of a flashlight that's set to the side of it and the shadow that it makes against the z-axis, right? And that's going to be according to the cosine of alpha, okay? Now let's think about this. Why is this such a good thing? Well, if we look at the component in the xy plane, mxy, and the component in the mz plane, and add them together, it's actually greater than m0. So think of the angle 45 degrees. The cosine and the sine of 45 degrees is the same, because it's from an isosceles right triangle, which is 0.7, right? So if I have 0.7 of m0 in the xy plane, and 0.7 of m0 along the z-axis, well, then I have 1.4 m0. I've increased my functional amount of total magnetization by 40%. How did that happen? Math magics. That's what I call it. Thank you. I've been sitting on that one for about 12 hours, thought of it this morning when I couldn't sleep. But yeah, without going into explaining why that is, it's one of those things that, just like David Copperfield or whoever that Blaine guy is, street magician, when you see it, you're like, that can't be possible. But obviously it's happening in the real world. It's just not immediately obvious why. But that's why this is actually, it's one of the reasons why this is good, and we can use it to such an advantage. All right, now let's talk about the actual rating of gradient echo imaging. Let's talk about T1. I'll try and keep it briefer than the initial discussions. I won't belabor every single point. The most important thing is a little tougher because there's actually two factors that play into the T1 weighting for gradient echo imaging, which is the flip angle, which is going to be the most important part, okay? With a small flip angle, the T1 effect is going to be minimized. With a large flip angle, the T1 effect is going to be emphasized. You can think about this kind of like in a spin echo, it was all about the TR. How much did we allow it to recover, right? Now, if you're using a very small flip angle, you're barely taking any magnetization out of MZ, which means that it kind of doesn't matter how much things regrow. So you're de-emphasizing T1. If you're using a flip angle of, say, 60 degrees, right, you're taking more than half of the magnetization out of the longitudinal plane with every RF pulse. Those are big chunks, big bites you're taking out of it. Big, large amounts of water you're taking out of the toilet tank for it to refill before the next TR, which you recall are much shorter in gradient echo imaging. So a large flip angle is going to be our primary thing that T1 weights gradient echo images. Okay. If you're a first year, or this is the first time you think about it, this will probably blow your mind if you've been following me up to this point. Actually, probably not. Only people like me. But you guys, I'm sure you're fine. Just be like, whatever. And go on eating your rat. Anyway, all right, so TR. A longer TR time emphasizes the T1 effect, and a shorter time minimizes it. Now, this boggled my mind forever because it's the opposite of spin echo sequences. You'll notice spin echo is the opposite. And the reason is because the entire time scale that we're working with in gradient echo imaging is so much shorter than with spin echo. With spin echo, we're talking about relatively long times, so it's all about the repetition time in terms of if you're not letting something recover, it'll destroy its weighting if it has a short T1 or a long T1 time. In gradient echo imaging, since we're operating on such a small time, and the primary determinant is how large the flip angle is, then it also is important how much you're waiting. Because if you're waiting a little bit longer, then you're going to allow things to recover a little more. So actually, having a slightly longer TR will emphasize the T1 effect when used in conjunction with a larger flip angle. It's confusing. Forget it. Just like, hear it, think about it a bunch of times, and slowly it'll sink in. Okay, TE, thank goodness, easy, same as spin echo, right? The longer you wait to collect the echo, the more stuff decays, and things with longer TE hold their signal for longer. So that's the same as spin echo. Now we end up with a slightly more complicated looking grid because I can't quite do it the way I did the other one. So we have to talk about it in terms of flip angle TR and TE, right? So the thing to note here is just remember what T1 weights it, right? A large flip angle and a long TR is going to T1 weight it, and then a short TE on T2 weights it, or de-emphasizes the T2 effect, okay? And then for T2 star, remember in gradient echo imaging, there's no 180-degree inversion pulse, so you're not getting rephased echoes. You're just looking at free induction decay. So it's always every signal is going to decay as T2 star instead of T2. Important point. All right. the flip angle is small and TR is short for both of these because you want to de-emphasize T1, right? So you've de-emphasized T1 in the T2 star with a small flip angle and a short TR, but then you use a long TE because that's where your T2 weighting comes from, right? You wait a long time, things with long TEs, T2s keep their signal. For proton density, same thing, you unweight the T1 by using a small flip angle and a short TR, and then you unweight the T2 by using a short TE. Everyone see the parallel there between spin echo? Oh geez, oh boy, sorry, got lost. There we go. Okay, now let's take a look at the individual gradients. All right, let's start with proton density. So I set the model to say that liver has 75% proton density of fat and CSF. So we're looking now, remember, for a proton density, we're going to be using small flip angles and short TRs to de-emphasize T1 effects. And we can actually see that in the longitudinal plane. These flip angles are so small that you're barely decrementing the overall longitudinal magnetization. So it's going to this is where you can kind of see that the T1 effects aren't really going to matter. I mean, you can see this very nicely, this proton density effect coming through, because the green, the liver is 75. Then when we look at the transverse magnetization over 5 different flip angles, we see that, we have to use, in order to get proton density, a relatively short TE. So we're unweighting the T2, right? Because if we waited a long time, then the T2 effects really take over, because fat and liver are taking a dive and CSF is staying relatively constant. So we have really bright CSF if we waited a while, right? But as long as we wait a short time, we've unweighted T1 on the top, we've unweighted T2 on the bottom. By default, we're looking at our relative proton densities, which comes across because CSF and fat are similar, and liver is about 75% of that, which is what we set the model to. Everyone follow that? Home stretch, I promise. My feet are killing me, so I'm sure you guys' butts are hurting too from sitting there and listening to me. All right, let's take a look at T1 weighted imaging. Okay, remember, in order to get a T1 weighted image, you want to have a larger flip angle and a longer TR. Now we're starting to see the same, on the top, the same thing that happened with the spin echo sequences, where CSF, or the fluid density things, the things with long T1s or bad T1s, are satting out. And that's because we're taking such big chunks out of it, right, that it's just not able to recover, whereas fat and liver are setting themselves up with a nice equilibrium of signal. Okay? Now moving into the XY plane, as we look over multiple things, we see that effect of the CSF dying out by the 5th RF pulse. And of course, if we're going to do a T1, again, it has to be a short TE in order to de-emphasize T2 effects. So we're looking close over here. And of course, it's what we expect to see from a T1 weighted image. The fat is about twice as bright as the liver, and the CSF is dark. Makes sense? Excellent. One more. T2. Again, we set all the proton densities to be the same. We're going to unweight T1 effects by using a small flip angle and a relatively short TR, right? So these things are all kind of clustered together. CSF's going down a little bit, but we see how that comes out in the XY plane on the bottom. The CSF is still relatively high, and especially if we wait a relatively long TE, let's say 75 milliseconds, since the TR, that's half the TR, which is 150, well, we're going to get really bright CSF here, which is going to be at least twice as much as fat, which will be gray, and liver will be relatively darker than fat. T2 weighted image, but much faster than the time of the spin echo. Okay, so review and contrast with the spin echo and gradient echo imaging parameters. Remember, for gradient, you have 3 things to consider, and there are 2 things that affect T1 weighting and unweighting, which is probably the best way to think about it. And yeah, so if you want, you can just, if it gets too confusing trying to reason through all of it, you can always just memorize these graphs. Let's do a couple of quick questions just to check our understanding. All right, so a gradient echo is performed with the above parameters, which are not showing up. Okay, above parameters. What type of weighting should the image have? All right, let's look at our weighting parameters. Flip angle is 10, right? Think of it as out of 90, so that's kind of small. The TR is 120. Now we're on a totally different time scale here than spin echo. TE is 100 milliseconds, which is definitely long. And I guess the TR is a little short. All right, so what type of weighting should the image have? SSFP, T1, T2, PD, or MRA? I'm going to think in silence so I can actually figure it out. Yeah, it's a small flip angle and a relatively short TR. With a long TE. I can't even figure out my own questions. How bad is that? All right, let's see what you guys said. T2, yes! Despite my trying to confuse everyone and getting confused myself, you guys got the right answer, which is it's a T2 weighted image, right? Let's refer to the thing. Right, a flip angle of 10 is small. The TR of 120 is relatively short, and the TE is relatively long. So, bam. Okay, next. Gradient echo with the following parameters.
Matrices.
One gradient echo per RF. So it's not a multi-echo gradient sequence. How long does it take to acquire one image? Salient numbers are the matrix size, which is 64 by 64, and the TR, which is 100 millisecond. Note, as expected, the next is 1. So that's, yes, about 6 seconds, right? So 6,400 milliseconds is about 6 seconds, right? So 6.4 seconds. It's just the number of phase encoding steps times the TR. Next, of course, as expected, is 1. All right. Now what type of signal weighting are we going to have here? Flip angle is 5. That's definitely low. The TR is 100. That's relatively low. And TE is 30. That's pretty short. That's pretty short. Yes, proton density. Very good. You all got it correct. So that's, oh, I already said it. Small flip angle, short TR, and short TE. Okay, one more about weighting. The flip angle is 60. Well, that's a lot bigger than the other questions. The TR is 800. That's a lot longer than the other questions. And the TE is 15. That's shorter than the other questions. Yes, 100% correct. T1 weighted, right? It's got a large flip angle and a relatively long TR, which is T1 weighting. It's got a short TE, 15 milliseconds, which is T2 unweighting. So the overall result is a T1 weighted image. Okay, now here's a gradient echo image performed with these parameters. I'll try not to confuse you. Assuming it's a multi-gradient, sorry, man, I'm getting that. Assuming it's a multi-echo gradient echo sequence, it's written wrong, with 4 echoes recorded per RF, how long does it take to get one image? Salient features, matrix is 64, TR is 1000, 4 echoes per RF, and as expected, next is 1. Yes, 100% correct. Hey. Wiseacre. Yes, it's about 16 seconds, right? So it's the number of phase encoding steps times the TR, which is 1,000 milliseconds is 1 second, times 64 is the matrix size and the phase direction, divided by the number of echoes per RF, which is 4. 64 divided by 4 is 16 seconds, exactly. And again, next is 1, don't forget that. For bonus credit, what's the weighting on this? Large flip angle, long TR, short TE. T1, very good. You guys are very good. Thank you for listening. We'll still got more coming next week, so we'll do everybody's favorite.
Thank you.
Thank you.